Welcome students to lesson 47. We are on your Thermodynamics chapter 12 in the OpenStax textbook. And today we're going to cover spontaneity, the conditions for spontaneity, and Gibbs free energy. Okay, so in review regarding entropy, the second law of thermodynamics, that tells us that the entropy of the universe is constantly changing. So when a process happens, entropy increases. All right, so we have here an equation that tells us that, for a process, we have a change in entropy. Okay, and it's possible in a process for some entropy, which is an energy form, to be converted to some heat. Okay, so in this equation, S is the entropy increase or decrease. For that process. And then this second term here is a little bit of entropy that can potentially be converted to heat, which is the Q term here. And T is temperature. All right, so the condition for being a spontaneous process, the second law tells us that going from order to disorder tends to be a spontaneous thing. So for the condition for a spontaneous process, okay, in this equation we're looking at, okay, for a spontaneous process, this S here is a positive value. There's an increase in entropy. So basically what that tells us is that the change in the entropy has to be bigger than Q over T. Okay, because this is a positive quantity, this has to be bigger than this. Okay, so that is the condition for a spontaneous process. Okay, so remember that the Q term here, if we are at constant temperature and pressure, the Q term is our enthalpy change. Okay, so the condition for spontaneity is for delta S to be bigger than delta H over the temperature. Okay, so we can rearrange this equation, multiply by T and subtract delta H. Or we could do it this way, go T delta S is bigger than delta H. And then if we subtract the T delta S term, then we get 0 has to be bigger than delta H minus T delta S. Okay, so basically flipping this equation, the quantity delta H minus T delta S has to be less than 0. So that is the condition for a spontaneous process, and it's summarized nice and neatly here in this equation. So I'm going to get rid of this stuff for now. Okay, so the condition for spontaneity, the quantity, enthalpy change minus temperature times entropy change has to be less than 0. And we are talking about at standard conditions. Okay, for a non-spontaneous process, the opposite is true. The delta S, okay, is going to equal the S plus the Q over T term. Okay, this time for a non-spontaneous process, this is a negative number. So that means delta S is going to be less than Q over T. And remember, the Q over T is delta H over T. And if we went through the same rearrangement process, we could arrive at this relationship here, that for a non-spontaneous process, the quantity enthalpy change minus temperature entropy change has to be bigger than 0. Okay, so that's positive. That quantity has to be a positive quantity. The condition for the spontaneous was the quantity delta H minus T delta S has to be negative. Okay, so this is the condition for a spontaneous process. This is the condition for a non-spontaneous process. And remember, if we are at equilibrium, okay, if you're at equilibrium, that means that this delta S equals Q, I'm sorry, let me change that, equals S plus Q over T. If you're at equilibrium, the entropy is 0. So this term drops out. And so basically, if you're at equilibrium, delta S is equal to the Q over T, so that's the enthalpy change over temperature for a constant temperature and pressure. And so this quantity, delta H minus T delta S, has to equal 0 if we are at equilibrium. Okay, so obviously the quantity of the enthalpy change minus temperature entropy change dictates whether a process is spontaneous or not. So the relationships we derived in the previous slide have defined for us a new state function. And this new state function is called Gibbs free energy. So Gibbs free energy is a new state function that we wish to consider. And as a state function, any change in a process, the change in the Gibbs free energy change, is going to be the final state minus the initial state. Okay, if we are doing a chemical reaction or process under standard conditions, that means any reactions are done at 25 degrees C. All pressures of gases, etc., technically 1 bar, which is pretty close to 1 atmosphere. Any solutions are at 1 molar, technically 1 activity unit. Okay, so that's the standard condition. All right, so any process change in Gibbs free energy under standard conditions is final state minus initial state. Okay, and for a reaction, remember, this is going to be the summation over all of our products, however many moles, the standard Gibbs free energy of formation minus the summation over all the reactants, however many moles of each of those, and the Gibbs free energy of formation for those processes. So once again, we have a new state function defined. It's Gibbs free energy change. And we can find that value from data tables for formation reactions and the thermodynamically determined values for Gibbs free energy. Okay, all right, so here is the equation we derived from our previous slide. Delta G is equal to the enthalpy change minus temperature entropy change. So very important thing to remember. And from the previous slide, if you'll remember, we said that a process is spontaneous when this quantity right here is less than 0. Okay, so for a spontaneous process, delta H minus T delta S is less than 0. And this is Gibbs free energy change. So whenever Gibbs free energy change is less than 0, that is Gibbs free energy change is negative, we have a spontaneous process. Okay? The reverse is a non-spontaneous process. Okay, for a non-spontaneous process, we said delta H minus T delta S has to be bigger than 0. This quantity is Gibbs free energy change. So anytime Gibbs free energy change is positive, we have a non-spontaneous process. And finally, if we are in a situation where delta H minus T delta S equals 0, okay, that means we are at equilibrium. So this is Gibbs free energy change. And so if that value is 0, we are at equilibrium. Okay, now that we've defined what Gibbs free energy is and the condition for spontaneity based upon the sign of Gibbs free energy change, we can start predicting values for the Gibbs free energy change from thermodynamic data tables. As you will recall in the past, okay, we have access to standard enthalpy of formation data for various substances. We also have standard molar entropy data for most substances. And so if we recall that Gibbs free energy change under standard conditions is equal to standard enthalpy change minus temperature standard molar entropy change, for a given process, if I can calculate the enthalpy change and the entropy change, and I know the temperature at which the reaction is going on, I can calculate the Gibbs free energy change. So we're going to do that in our first example. So we want to use standard molar enthalpy of formation and entropy data to predict the Gibbs free energy change of the following reaction, and we want to know if it's spontaneous or not. Okay, so let's look at the reaction. The first critical step is to make sure we have a balanced chemical equation, because all of our data tables over here, these are all molar quantities. Okay, so balancing, looks like we have combustion of methane to CO2 and water. Notice the product is liquid water, not gaseous. That's important when we look up values in the thermodynamic table. Okay, so let's get to balancing. I have 1 carbon left, 1 carbon right. Hydrogen, I have 4 left, so I'm going to need a 2 out in front of the water molecule. And oxygen on the right, I now have a total of 4. So I'm going to need a 2 out in front of the oxygen. All right, so I'm balanced. So now I can get to work with predicting delta H and delta S values. So starting with the delta H, so summation over my products, I have 1 mole of CO2 gas. That is negative 394. And units here are kilojoules per mole. I have 2 moles of water in its liquid state, so I'm going here. And there's the delta H, negative 286. Summation over my products. Now I subtract off summation over my reactants. 1 mole of methane gas, delta H, negative 75 kilojoules per mole. Okay, and remember oxygen is in its standard state, so that delta H value is 0. Okay, so for the enthalpy change of this reaction, I come up with a value of negative 818.9, and the units, moles, are going to cancel throughout all these calculations. So this is kilojoules. So there's my enthalpy change. Okay, notice it's exothermic. Okay, exothermic tends towards spontaneity. Okay, but we must consider entropy before knowing overall if this is going to be spontaneous or not. All right, so I'm going to do the same thing for my entropy change. Summation over the products. 1 mole of CO2. Okay, so let me clear away some of my annotation here. Okay, so CO2 gas entropy is a positive 214, and notice the units are joules per mole Kelvin. Okay, I have 2 moles of water in its liquid state, 70 joules per mole Kelvin. And now I have to subtract off. Summation over my reactants. Methane, 186. And I also have 2 moles of oxygen. Notice the entropy of O2 gas is not 0. It's 205 joules per mole Kelvin. Okay, so my entropy change for this reaction comes out to be a negative 72.16 kilojoules. I'm sorry, I'm back up, not kilojoules. Let's look at our unit analysis. Moles cancel, we're left with joules per degree Kelvin. Okay. So, notice the sign on the entropy change. Entropy decreased. That tends to be non-spontaneous. We had a decrease in entropy. Okay, let's rationalize why we had a decrease in entropy. Let's do an analysis of how many moles of gas in our reactants and products. If you look at the balanced equation, we had 1 and 2, a total of 3 moles of gaseous reactant, and it went to a total of, since this is liquid, we really went to 1 mole of gaseous product. Okay, so we had a decrease in the moles of gas, which is the most random state. And so that would help explain why entropy is decreasing in this reaction. Okay, so overall, we want to know if this process is spontaneous or not, and what is the value of the Gibbs free energy change. So to get that overall Gibbs free energy change, I need to make use of the fact that that is equal to the enthalpy change minus temperature entropy change. Okay, delta H, negative 818.9 kilojoules minus temperature. Okay, because we are making all these measurements under standard conditions, that means temperature is 25 degrees C, which on the Kelvin scale is 298 Kelvin. So this is 298 Kelvin multiplied by our entropy change, negative 72.16 joules per degree Kelvin. Okay, notice we have a unit problem. Enthalpy is in kilojoules and entropy is in joules. So I can convert one or the other. If I want to get the entropy term into kilojoules, I have to divide by 1,000 joules per kilojoule. Okay, so with that calculation, and I'm going to come back up and change my value on my enthalpy change. I copied the wrong number. Let's come back and do this again. It should be negative 891 kilojoules. So down here, this should be negative 891. There we go. All right, so now I have the correct enthalpy change value in there. And so when I plug in these numbers and do the math, I come up with, and this is where I had that previous number, the Gibbs free energy change is going to be a negative 818.9 kilojoules. Okay, because over here in this other term, degrees Kelvin canceled. Joules cancel and kilojoules come up into the numerator. Okay, so there's your Gibbs free energy change. Okay, so now we need to ask, is it spontaneous or not? And that has to do with the sign. Delta G is negative. If delta G is negative, it's spontaneous. And this is a pretty big negative delta G. So this is very spontaneous. Okay, so it's a very good illustration of how we use thermodynamic data tables to predict spontaneity of reactions and the dependence on the enthalpy change as well as entropy. In this case, it was enthalpy favored, but entropy was not favored in this reaction. What we wish to do next is predict whether a given process is going to be spontaneous at all temperatures, at no temperatures, or at higher low temperatures. So what we want to do is just look at our equation for the Gibbs free energy change up here and just think through the mathematical relationships. Okay, so first scenario, what is the situation on spontaneity? If my enthalpy change is positive, my entropy change is positive, okay? So we just want to think about the sign. So if delta H is positive and delta S is positive, notice that the delta H term is always going to be positive. So that we say that tends toward being non-spontaneous. Okay, because delta G's got to be negative to be spontaneous. Okay, so the only way for delta G to be negative, spontaneous, is if this term is small and this term is big. Okay, so in order for Gibbs free energy change to be negative, spontaneous, okay, that's only going to happen when that second term is big, so that's at high temperature. Okay, so in terms of all temperatures, is it spontaneous? It depends on the temperature. And once again, the Gibbs free energy change, it could be plus or it could be minus. It could be spontaneous or not spontaneous, depending on the magnitude of the delta H value and the delta S value and the temperature. Okay, next analysis. What happens if we have an exothermic reaction? Remember, negative is exothermic. And we have increasing entropy. Okay, so exothermic and increasing entropy. So the sign on delta at LH is negative, and the sign on delta S is positive, but in this equation there's a negative out here. So this term is negative, and this term is always negative. What that means is delta G is always negative. Okay, if delta G is always negative, it is always spontaneous. It is spontaneous at all temperatures. Pretty cool. All right, next one. What if okay, next situation. Let's say our reaction is endothermic. It's positive, the delta H, and we have decreasing entropy. So delta H is positive, delta S is negative, and notice the second term, because we're subtracting a negative, the second term is positive. So there is no way for delta G to ever be negative. There is no way for delta G to be spontaneous. Okay? In that case, delta G is always a positive value. It is never spontaneous. So it is never spontaneous at any temperature. This reaction is always non-spontaneous. The above one was always spontaneous. Doesn't matter what the temperature is. That process is always spontaneous. Okay, and the last one for consideration. Okay, what if we have a situation where we have an exothermic process that tends to be spontaneous, but we have a decrease in entropy that doesn't tend to be spontaneous? All right, so now we do the sign analysis. So this term is always negative. This term, it's minus a negative. So minus a negative means this term is always a positive. Okay, so in order for delta G to be negative, spontaneous, okay, we want this term to be bigger than this term. Okay, so that means we want low temperatures. So this scenario is a process which will depend on the temperature, and if we have low temperatures, then it's going to tend to be spontaneous. So that's the sign analysis on the Gibbs free energy change equation, and whether or not a process is predicted to be spontaneous at any temperature, no temperatures, high temperature, or low temperature. Okay, so the next important thing we want to think about is for the processes in which the Gibbs free energy change and its sign, whether it's spontaneous or not, has a dependence on temperature. So remember, for an exothermic process that entropy increases, Gibbs free energy change is always negative. It's always spontaneous, and it's spontaneous at all temperatures. When enthalpy change is endothermic, and we have decreasing in entropy, that is one in which delta G is always positive. It is always non-spontaneous. Non-spontaneous, always. And so it is never spontaneous at any temperature. Okay? All right, so we want to think about these other cases here in which there is a temperature dependence. So once again, when delta H is positive, that tends to be non-spontaneous, but entropy is favored. That means this term is negative. So it's when this term is big is when it's going to be spontaneous. So that's at high temperatures. Okay, the reverse is true for the scenario down here. If we have an exothermic process, that tends to be spontaneous, but if we have decreasing entropy, then this term, it's minus, darker color here, it's minus a negative term, so this becomes a positive term. That's tending away from spontaneity. Okay, so in order for delta G to be negative, we want delta H to be big compared to this term, so we want low temperature for spontaneity. So here it depends on the temperature, it depends on the temperature. Okay, what I want to do on this slide is predict the temperature at which we go from either spontaneous to non-spontaneous or vice versa. Okay, what is that critical temperature for these cases? Okay, let me do this again. For this case here, and this case here, whether it's spontaneous or not depends on the temperature. Okay, so we want to predict what is that critical temperature where we change from spontaneous to non-spontaneous or vice versa. All right, so let's just rewrite our equation. Gibbs free energy change is delta H minus T delta S. Okay, so remember, to be spontaneous, delta G is negative. That's spontaneous. If delta G is positive, that's non-spontaneous. And notice that to go from spontaneous to non-spontaneous, to go from negative to positive, you got to go through 0. Okay, so if we set delta G to 0, that is going to be the critical temperature where you transition from spontaneous to non-spontaneous. So rearranging this equation, you're going to have delta H is equal to T delta S, or in other words, this critical temperature where you go from spontaneous to non-spontaneous is going to be delta H divided by entropy change. So here's your critical temperature for these two scenarios where you transition in spontaneity. Okay, so what I want to do now is take our previous problem in which we had looked at this given reaction, the combustion of methane. We used thermodynamic data tables to predict the enthalpy change. It was exothermic. Okay. We predicted the entropy change right here. We had a decrease in entropy. And we predicted the overall Gibbs free energy change of this process under standard conditions to be a pretty large negative value, so very spontaneous. Okay, so when we talk about this reaction, we like to ask, is this reaction enthalpy favored? In order to be enthalpy favored, delta H has to be negative. That is what we call being enthalpy favored. And in this case, it is. So yes, it is enthalpy favored. Is this reaction entropy favored? Is the spontaneity of this reaction entropy favored? Okay, we did the analysis on moles of gas. Remember, we went from 3 moles of gas to a total of 1 mole of gas. And so we know this is not entropy favored. The sign on delta S here is negative. So that means we are not entropy favored. Okay, all right. So the other critical question, since we are in one of these scenarios where we are enthalpy favored but not entropy favored, what is that critical temperature at which we go from being spontaneous to non-spontaneous? Okay, and this is the scenario where, remember, delta G is delta H minus temperature delta S. In this case, we are enthalpy favored. This is exothermic. And entropy is not favored. It's negative. Okay, so notice that this term is negative, tends to be spontaneous, but this term is going to become a positive value. The bigger temperature gets, the bigger that term becomes, and the reaction will eventually become non-spontaneous. So what is that critical temperature? All right, so that's our next question that we want to solve here. So I'm going to get rid of some of this annotation. Give us some room to work. Okay, now we're ready to go. So by definition, when we're spontaneous at lower temperature, but we become non-spontaneous at higher temperature. So what is that magical temperature where we go from spontaneous to non-spontaneous? All right, so once again, that happens when delta G goes from negative to positive, and you have to go through 0. So 0 equals delta H minus T delta S. The magical temperature is delta H over delta S. Okay, and so just plugging in our values, negative 891 kilojoules of energy for the enthalpy change. Entropy change is negative 72.16 joules per degree Kelvin. Okay, we need to get one of these over to the other form. So there are, I'm going to come up here and I'm going to multiply by 1,000 joules per kilojoule in my numerator. Okay, all right, so carrying out the math here. Okay, notice that the negatives are going to cancel, so we have a positive temperature. Units, kilojoules are canceling, joules are canceling, Kelvin comes up into the numerator. Perfect. We're trying to calculate the temperature, magical temperature at which this happens. Okay, wow, and what a value, 11,348 degrees Kelvin. that is a really high temperature. So this reaction is going to be spontaneous at all temperatures, all temps between 0 Kelvin and 11,348 Kelvin. It becomes non-spontaneous at temperatures greater than that temperature. All right, so it's pretty safe to say this is going to be a spontaneous reaction at most reasonable temperatures. Okay, so different ways that we can calculate the Gibbs free energy change for a reaction and predict if it's going to be spontaneous or not. Some of you in the previous example were probably going, well, why did we use the equation with the enthalpy and the entropy when I could have gone directly to the Gibbs free energy change in the table to predict the change in delta G? So, as we previously stated, if you do have access to thermodynamic data for the Gibbs free energy change for formation reactions, yes, by all means, you can sum up over your products the number of moles of substances with the delta G values and then subtract off the summation over your reactants. Okay, just like we've learned to do before. So if you do have this data available to you, by all means, you can calculate this directly. So here's another example. We want to predict the Gibbs free energy change of this reaction under standard conditions. Okay, so as always, let's balance this reaction. We've got 1 carbon left, 1 carbon right. We currently have half of a molecule of O2, so we have 1 oxygen and 1 oxygen over here, so 2 oxygen and 2 oxygen there. So this reaction's balanced. No work for us here. Okay, awesome. All right, so Gibbs free energy change. We can calculate the delta G, starting with products. I have 1 mole of CO2 gas. So CO2 gas, delta G, negative 394 units, kilojoules per mole. Only 1 product, this one's easy. 2 reactants. I have 1 mole of carbon monoxide gas. Here's carbon monoxide gas, there's the delta G, negative 137 kilojoules per mole. Okay, and Gibbs free energy of formation is like enthalpies of formation. If you have a substance in its standard state, the value is 0. So the oxygen term has a value of 0 here. So very simply, my Gibbs free energy change for this reaction under standard conditions comes out to be a negative 257 kilojoules. Moles are canceling in this equation. All right, so is it spontaneous? It's negative, so this reaction is spontaneous. Okay, you could predict the temperature dependence if you wanted to by going through and calculating delta H and delta S and figuring out if it's enthalpy favored or entropy favored. I'll let you do that on your own, and if it has a dependence on temperature or not. Okay, and here's where we finally start tying things together. We spent, I don't know how many weeks talking about equilibria and equilibria systems and the importance of the equilibrium constant. So reactions that are favored have large equilibrium constants. If you will, if I have some reaction okay, and the forward process is favored, my concentration of products in the reaction mixture are very large. The concentrations of the reactants are very small. If the reverse reaction is not favored at all, then K is large. Okay, all right, so let's tie this concept to our understanding of spontaneity. Spontaneous reactions are going to be those in which the forward reaction is favored. Okay, we're going to have a reaction that goes. We mix the reactants and it just goes. We don't have to do work to make the reaction go. Okay, non-spontaneous processes are going to be those that when we mix the two reactants or three, it just sits there. We would have to do work to make that reaction go. Okay, so we want to start deriving a relationship between our criterion for spontaneity, that's delta G, and the equilibrium constant K. All right, so to do this, we are going to start with this equation up here. Okay, so everything we've discussed thus far has been measuring the Gibbs free energy change under standard conditions. Remember, that's at 25 degrees C and 1 atmosphere pressure for gases, etc. Well, the reality is most reactions are not conducted under those conditions, but other conditions. So if we want to predict a delta G under non-standard conditions, we have to put a correction term into this equation to account for differing concentrations or pressures of the gases or differing temperature. So in the equation we're looking at up here, this term over here, this RT ln Q, this is a correction factor for the fact that we're not at standard conditions. Okay, Q is the reaction quotient that we have worked with before. The non-equilibrium concentration of our products and reactants, similar to how we write the equilibrium constant, but if we're not at equilibrium, if we're at some initial concentrations of these species, or concentrations of these species that are not 1 molar, that would become our reaction quotient value. Okay, so to correct for being at temperature other than 25 Celsius, etc., we have this equation. Okay, if we are, by definition, if we are at equilibrium, Gibbs free energy change goes to 0. Okay, all right, so if we are at equilibrium, we now have this equation, which I can rearrange. If I subtract this term from both sides of the equation, I get Gibbs free energy change under standard conditions is equal to negative RT ln, and if we go from not being at equilibrium to being at equilibrium, Q becomes K. All right, so here's a great equation that directly relates the Gibbs free energy change to our equilibrium constant K. So you can calculate delta G if you know what K is and you know the temperature. The R here in this equation becomes 8.314 joules per mole degree Kelvin. Okay, it's up here, it's in kilojoules, so that's why the decimal places are off there. Okay, so important equation allows us to calculate delta G if we know K. If we want to do the reverse, you need to solve this equation for K mathematically. Okay, to solve for K, you must raise e to this exponent on both sides. Okay, so in doing so, back up. Just a second. Let me rearrange first. Okay, first of all, let me do this. Natural log K is going to equal, divide both sides by the negative RT term. There we go. Now we want to raise e to this exponent on both sides of the equation. When you raise e to the ln k, you get out k. Okay, and that's going to equal e to the negative Gibbs free energy change under standard conditions over RT. That's your exponent. Okay? All right, so if you have access to the thermodynamic data tables and can predict the Gibbs free energy change for a reaction, we know R is the gas constant, 8.314 joules per mole Kelvin, and T is your temperature in Kelvin. So we can now calculate a relationship between K and Gibbs free energy change. Now that we have that all-important relationship between Gibbs free energy change and the magnitude of the equilibrium constant, we want to think about the different conditions and signs on these values to rationalize spontaneous processes. Okay, so once again, a spontaneous process is one in which when we mix the reactants, okay, the reaction goes. We have a big equilibrium constant. The concentration of the products is huge. The concentration of the reactants is small. Okay, so, you know, if it's spontaneous, we should have a very large K. The bigger K, the more spontaneous. The smaller the K, the more non-spontaneous. So if it's non-spontaneous, the equilibrium is little forward, big reverse. K is going to be very small. Okay, so let's go to our equation. We said that, remember, Gibbs free energy change under standard conditions equals negative gas constant temperature natural log of K. All right, so our analysis of spontaneity and the relationship of delta G and K. All right, if delta G is negative, that means we have a spontaneous process. So from a mathematical perspective, for this term to be negative, notice there's a negative out front here, so you want the ln K term to be positive. Okay, so spontaneous processes are those for which the natural log K term is positive, and that's only going to happen when K has a value that's bigger than 1. Okay, that's going to be the scenario. Equilibrium constant is bigger than 1. That means the concentration of your products in the equilibrium term is bigger than that of the reactants. And that makes sense, right? So our mixture at equilibrium is mostly product. Forward reaction goes without us having to do work. Okay, the opposite scenario. If Gibbs free energy change is positive, this term up here is positive, that means we have a non-spontaneous process. Okay, so what kind of equilibrium constants would give us that? Well, since this term is negative, if this term were also negative, then the overall term on the right would be positive. So that's going to be the scenario. When natural log K is negative, we're going to have a non-spontaneous process. That happens when the value of K is less than 1. So this ratio of the concentrations is less than 1. So that means you have very little product, mostly reactant, and that's a non-spontaneous process. So very important relationships between these variables, and an understanding of what a spontaneous process is. Okay, you mix these reactants. If it's spontaneous, it goes, you get a lot of product, and most of this is gone. The bigger the K, the more negative is the delta G. Okay, and then the opposite is true. If you don't have a spontaneous process, that reaction does not go, and you have no product and mostly reactant. Okay, so the final thing we want to be able to do in this chapter is predict values of the equilibrium constant K if we know what the delta G is, or you could do this vice versa. So let's go back to our reaction of the combustion of methane. Okay, if you'll recall, under standard conditions, we calculated these variables. The enthalpy change was exothermic, large negative exothermic value. The entropy change, we actually decreased entropy. Okay, and so decreased entropy here. Okay, and the overall Gibbs free energy change, however, was a very large negative value, so it's very spontaneous. Okay, very spontaneous at temperatures lower than 11,000, whatever it was. Very high temperature at which this thing becomes non-spontaneous. Okay, all right, so what we want to do now is predict the value of the equilibrium constant from our known thermodynamic data. Okay, all right, so we're just going to use our equation of, remember, delta G0 is equal to negative RT natural log K, or if we need to solve for K, that's going to be e to the negative delta G0 over RT. All right, in this question, we're wanting to predict the equilibrium constant at 100 degrees C, so we're not at standard temperature, but that's okay. I can use this equation to predict that value. All right, so K is simply going to be e raised to the negative Gibbs free energy change. You get that from the thermodynamic data tables, and that is in kilojoules. Okay, I'm going to divide by the gas constant, which is in joules. So I'm going to multiply by 1,000 joules per kilojoule. In the denominator, gas constant R, 8.314 joules per mole degree Kelvin. And the temperature in this case, we were predicting equilibrium constant at, okay, Kelvin is degrees Celsius plus 273. This is 100 plus 273, so we are at 373 Kelvin. Okay, so in this equation, we are raising e to the exponent a positive 264. That's huge. We come up with a value of 4.8 times 10 to the 114th. Okay, that is enormous. So we have an enormous equilibrium constant. Reaction goes to completion, no questions asked. At reasonable temperatures, remember, it only becomes spontaneous at incredibly high temperatures. Okay, all right, so there is the utility of the relationship between Gibbs free energy change, the ultimate predictor of spontaneity, and the value of the equilibrium constant. Two very important aspects of chemical reactions, and whether it's going to be feasible for the reaction to go without us having to do work. Thank you very much, and I look forward to seeing you soon.